Can everybody hear me just fine? Okay. Hello. This is work with Bob Carpenter, and I'm going to start out by bringing up a quote from Mark Liberman about, in order to have you think about why does annotation matter. Without lengthy iterative refinement of guidelines and equally lengthy iterative training of annotators, the level of intersubjective agreement on simple tasks of phonetic, phonological, syntactic, semantic, and pragmatic annotation is shockingly low. This is a significant practical problem in speech and language technology, but it poses questions of interest to psychologists, philosophers of language, and theoretical linguists as well. Let's consider word sense annotation. In a large word sense annotation resource project that I was part of, I'll be talking about some of our examples. And like many NLP annotation tasks, it has categorical classes and a highly skewed distribution where one class may get 70 to 80% of the examples, and then each next class has a smaller percentage. Unlike many NLP annotation tasks, however, it's got a very large number of labels in this sense that each word has a distinct set of labels. So if you get annotators together to do lots of words, they have to learn many, many different categorical classes. And can we expect equally good judgments on all words? Well, psychometric studies suggest that an individual's performance on a conceptually similar task will vary across semantic domains. So I kind of expected this result that I'm going to show you next, but many people are surprised by it, which is that for some words, like the word hi, we got very good pairwise agreement of 90%, and very good chance-adjusted agreement of 84% on a word hi with 7 senses. And this was 4 annotators doing 100 randomly selected instances from a heterogeneous corpus. But take another word, ask, with actually fewer senses, and the pairwise agreement was shockingly low in Mark's words, and Krippendorf's alpha was shockingly low. Well, what can we conclude from this? Not a whole lot, except that words with moderately many senses can have high agreement and they can have low agreement. And the same annotators can have different agreement levels on different words. And so the questions that I present now are, which instances are good? Does it depend on the sense label? Which one of the classes for a given word? Does it depend on the context of the word? Well, how can we answer these questions? Not very well with agreement metrics because they don't tell us very much, perhaps with a good model of the data, and that's what I'll be talking about here, although I won't really be able to answer all those deep questions. So first I'll talk a little bit about current annotation practice, and then I'll present this model, a generative model that has been around since 1979, and a case study where we repeated the word sense annotation that had been done with trained annotators using Amazon Mechanical Turkers, and I'll compare the data from the trained annotators with that, mention a few limitations, and then conclude. But before I really get into things, I want to present just a notation convention. I'm going to be using I for the items to be labeled, J, annotators, K, classes. I'll use that throughout the talk. So in annotation best practices, as many of us all know who've been doing this for a while, you design the annotation task, and this is going to repeat some of what Mark said. You write the guidelines. You have J annotators annotate a random sample of I items with their K classes. You measure their agreement, and if the pairwise agreement is 90% and the chance-adjusted agreement is above 67%, you're done. And otherwise, you go back, you refine the annotation task, you revise the annotation guidelines, and so on. Now, agreement metrics range, pairwise agreement is in 0, 1, chance-adjusted agreement is in -1, 1. And one question that comes up often, and that our session chair has written a lot about, Massimo, is how good is good enough? And that really depends a lot. But in addition to not having clear consensus on these threshold levels, there are many other issues. One is that these agreement metrics measure consistency and not accuracy. And I'm going to be talking about accuracy a lot here. Now, the assumption is, kind of unstated, that there's only one way to be right. So if your annotators agree, well, they must be right. As we say in the paper, and I won't go into at length here, there are factors that can lead to annotators agreeing when they shouldn't be agreeing. And then, what about when they don't agree? Do you just throw out that item because they didn't agree? Well, maybe one of them was right. Or maybe one of them was giving you some information, but you don't know that. Because the agreement metrics don't measure annotator differences, they don't measure differences across the different categories that are being used, or differences among items. There's a long list of limitations that we mention in the paper. I will say that I've used these agreement metrics myself for years, so it's not like I'm trying to completely get rid of them. But they are very limited, and we should recognize what they tell us and what they don't. One example limitation is the paradox of kappa, which is very typical for our data that we use in this field that's highly skewed, that you can get very good agreement on the majority class item. And then you're going to get very low chance-adjusted agreement, because chances are very high that you're going to get that agreement, and so there's nothing left to be above chance level agreement. That was called the paradox of kappa by Feinstein and Cicchetti in 1990. Also, people don't often compute confidence intervals for the agreement metrics, and when we do that, Bob and I noticed that the confidence intervals typically span the decision boundaries for what counts as good versus bad agreement. So now let me turn to the second part of the talk on the model that was originally presented by David and Skaney in 1979, and I believe that was actually dealing with the binary classes, which we're using, many classes, categorical classes. The goal was to determine consensus among doctors on patient histories, and it was a probabilistic model that generates the observed labels, the ground truth labels, the annotator accuracies and biases, and the category prevalence. Here's a plate diagram, which I included mainly just to have some variety in the slides. And the model, so that we've got the parameters. The Z is the true labels, pi is the prevalence of the labels, and theta are the annotator behavior. And we draw the true labels and the observed labels from a categorical distribution, and the other parameters from Dirichlet. For model inference, we do expectation maximization to get the maximum likelihood estimates, and we used weak Dirichlet priors for arithmetic stabilization because there would be cases where an annotator failed to use a given sense. Now, I'm going to now turn to just giving you an example that is based on the issue of accuracy that I brought up earlier. So here's Bayes' rule, that the posterior probability is proportional to the prior times the likelihood. And I'm going to work through this example now where we have two classes. The labels are 1 and 2. The prevalence of one is 20%. The prevalence of the next is 80%. And 3 annotators, theta 1, 2, and 3, with their confusion matrices. And we can see that annotator 3 is much more accurate because 90% of the time that annotator 3 picks 1, the truth was 1. So this is a hypothetical example, assuming that we know the truth. And one of the issues with collecting annotated data is it's kind of circular. We're trying to get the ground truth labels, but we don't know the ground truth labels, so how do we know when we're right? But that's why a model that's trying to jointly estimate all these parameters is appealing. Now, when this annotator picks 2, 80% of the time, that was the correct answer. So this annotator is much more accurate than the other 2 annotators. But what if the most accurate annotator disagrees with the majority? So we have Y1 picks 1, Y2 picks 1. So the majority label is 1, but Y3 picked 2. I can't go through all the math, but you can work it out, and it's in the paper. The probability, the conditional probability that the true label is 1, conditioned on the observed labels and the accuracies and the prevalence, is this product of the prevalence which is 20%, times what the first annotator, how often the first annotator is right when they pick one, how often the second annotator is right when they pick one, and how often the third annotator is picking one when it was really two. And here, these are the products that you get, and then you normalize it, and you find out that the probability that you get, the probability that the true label is 1, based on the observations and the parameters and so on, is 0.11, but the probability that it's 2 is 0.89. So because of that third annotator who's very accurate, even though 2 annotators voted against that annotator for the first label, the likelihood, the probability is that the true label was 0.89. So that's sort of a mini illustration of what's going on here and how we can try to get better ground truth labels. In the masked word sentence corpus, we had 116 words that had been picked by a panel of people that included a number of people with Christian Fellbaum from WordNet, and we were looking at the WordNet sense inventories along the way. So we had 29 adjectives, 44 nouns, and 43 verbs. And we used WordNet 3.1 sense labels. WordNet 3.1 wasn't out yet. We were taking the sense labels from WordNet 3.0, and we didn't have the resources to iterate over and over and over again for each word. But what we did do is we iterated once for each word, and sometimes we revised the sense inventories, and those sense inventories then became part of WordNet 3.1. The average number of senses per word was 7.2, but there was a very large range. So we were not looking at the, those ridiculous cases from WordNet where there's 50 senses, but we had a nice range. And for each word, we picked 1,000 sentences, trained annotators, more details about that in the paper. For each word, with 1,000 sentences, at least 100 sentences were done by approximately 4 annotators. And this is a big project, and so sometimes we had more annotators, sometimes we had fewer, and we tried to make sure all the annotators did everything, and in a few cases they didn't. But that was the general case. And then we saw that kind of variation that I pointed out at the very beginning of the talk, where very often we had very good agreement, and just as often we had pretty bad agreement. So I decided I wanted to do this crowdsourcing experiment with Bob, and we collected our data from Amazon Mechanical Turk. I'll go into how we designed the task a little bit more later. We picked 45 of the masked words randomly, and so we get the same distribution over parts of speech. We used the same WordNet sense inventories, largely the same sentences, but we had started this before the mask project was done, and so it turned out that we were picking from the same pool of sentences, but we didn't end up with exactly the same sentences in all cases, but by and large part we did. And each hit that an annotator, a Turker was faced with had 10 sentences for a given word, and there were 10 hits for each word, so there would be 1,000 sentences that way. Now for quality control, we went through iterative design of our hits. So we iterate a lot. 3 pilot studies and extensive discussions with Turkers on Turker Nation, who seem to really appreciate this. And so they helped me design the hits. And the final design used a hit title that I selected to appeal to people who like to read dictionaries, people like me, for American English word mavens. If you know what that means, then you probably are word maven, so you would like doing this task. Turkers with 98% lifetime approval rating, which is pretty high, but especially 20,000 approved hits. And we had Turkers emailing us. Actually, I handled all the email, so because I kind of like doing that sort of thing. And they would say, oh gosh, I'd love to do your hits, please let me. And they'd have 10,000 approved hits. But we had to hold fast, so I'd say, well, maybe someday we'll have some hits for you, but not these. Hits were automatically approved in 15 minutes, but we were monitoring the agreement with the current majority vote all along the way so that we could see whether we would have outliers who were just really not looking like they were doing normal word sense judgment. And we ended up blocking 5 Turkers out of 228, so that's not very many, so this seemed to work fairly well. And we actually unblocked one of them who begged us to do it again, because it turns out people who like to do this kind of thing really like to do it, and they don't see a lot of it, and so they when we were done, people would say, oh, please, can we do some more of your bits? No, sorry, it's all done. Unless somebody wants to fund us to do more of it. Now, here's some results I'm going to go into. I'm picking the verb help, which had very poor agreement, and it had 8 senses in WordNet 3.1. This is one of the words that got revised, because it used to have 9 when we first looked at it. The trained annotators used 6 senses. The Turkers used all 8. And the interesting thing here, the bars are colored in this way. The sense frequencies are on the x-axis. And the most frequent sense in the trained annotator data is the mask freak. That's blue. Then there's the Turker majority vote. And then there's the maximum likelihood estimate. And you can see that the sense 1 is way overestimated by the prevalence just by using frequency in the mask data or the majority vote. And that's because of this phenomenon that I just pointed out to you, that sometimes accurate annotators don't agree with the majority. So here's an accurate annotator from this particular word. If you look at other words that had better agreement, you'll get many more of these kinds of heat maps. But what we're showing is the response on the x-axis, the reference on the y-axis. And that means that if it's dark along the diagonal, those are the accurate cases. So this annotator was pretty accurate on 1, sense 3, sense 4, sense 6, and so on. Here's an annotator that had a huge bias for sense 1. And this happened enough that we got an overestimate of the prevalence of sense 1 just using, counting how often it occurred. But this annotator was very accurate on sense 4 for some reason. See, there's a nice black thing there. So you don't want to throw out all the information just because an annotator might be inaccurate. I mean, if you can use the information that annotator is accurate on a particular label, that's very useful. But it's also useful if you know that an annotator is biased in a particular direction away from something, and every time it's sense 2, they pick 1. That's still information. So that's something that you can get out of this kind of a model that you can't get out of agreement metrics. And here I'm showing that for this word, where we got pretty bad results with the agreement metrics and trained annotators, the thing that frustrated me was, well, we'd done all this work and then we had all these annotations, but which ones could we use? We didn't know anything about the individual items, but here we get a confidence measure for each item that gets labeled. And this table is just showing all the cases where the confidence was above 99%. And 80% of the cases were very confident. There was one label that was very confident. And here I have some examples to go back to in case anybody wants to about the senses 1, 3, and 6 that were very, the more frequent ones. But I want to compare the trained annotators with the Turkers. And I've got 2 colors of bars here, the trained versus the Turker plurality. There wasn't always a majority, so we're calling it the plurality. But there was often a majority, but one of the things that Bob complained about was that there wasn't as often a strong majority as he expected. I was chatting with Massimo before the talk, and we both kind of smiled and smirked because we do a lot of semantic and pragmatic annotation where that's not uncommon that you don't have a really strong majority even when you use a lot of annotators. Because, well, that's something I can't go into at length here. But these words are the words that showed the lowest proportion of cases where the trained annotator agreed with the Turkers, either using the plurality or the model. And you notice that they tend to agree with the plurality more than with the model. So with the word book, 80% of the time the trained label agreed with the plurality label, but only 60% of the time with the model label. And so that's just a way to illustrate how the 2 data sets line up with each other. The cost-benefit analysis is also very interesting to me anyway. The trained annotators produced data that cost us 70 cents per label. The Turkers gave us labels that only cost 33 cents per label, so less than half the cost. So it's lower cost and more information. And I think that's a win, although there are some limitations. For one thing, it assumes that there's a single ground truth label, and for word sense annotation, for certain kinds of words, I don't think that's necessarily the case. So we would need a different kind of modeling approach. We didn't really evaluate the quality of the model. We would need to build different models and compare them to really do that well. And we didn't look at item difficulty effects, which is something that we really want to do. That's why we collected so many labels per item, so that we could do that. So this is not the be-all and end-all. There are limitations here, but we do think that it's suggestive of a lot of information that we can be getting out of our annotated corpora. So in conclusion, this was a case study of word scent annotation where we got higher quality labels at lower cost for more information. And these models of annotation data that are generative have been used in the medical and epidemiological literature for quite a while. They're beginning to be used more in NLP, and I think there's a big benefit to that. I'll just conclude by pointing out that all the raw data of the annotations are available publicly, and the code, the R code for estimating the ground truth labels for the crowdsourced data is available from Bob Carpenter's Anno repository at GitHub. Thank you.
To our speaker, one thing that I forgot to mention at the beginning of the session is that I don't know if the paper is included in the proceedings, but this is a TACL paper, so you should be able to, if people want to read it, you can find it in TACL. So there is time for questions. Are there any questions?
Hi, thanks for the nice talk. So I would expect that the quality of Mechanical Turk labels would vary a lot with the number of annotators you have. So I was wondering if you evaluated that dimension as well.
If what?
The quality of Mechanical Turk labels would vary a lot with the number of annotators you have. You
mean doing something like filtering out half of our data and seeing...
Exactly,
but,
yeah.
I think if we did random selection of, filtering out some of the data, it would depend a lot on the words. So we still saw something like a division of 50-50 between words that just seemed to have, better consistency among the Turkers and words that didn't. And I think on some of these words, we could cut we really didn't need as many annotators as we had. I think we would have gotten the same quality with 10 annotators per label, because all we were estimating was the ground truth label and the prevalence and the annotator accuracy. I mentioned that we collected this many labels because we wanted to also look at item difficulty, which we ended up not doing yet. With 10 annotators, I think we would have gotten the same quality. With 5, I think it would really depend a lot on the word and on the sense, because there were some senses that were much more rare.
Would you be able to briefly summarize some of the things that you learned from discussions with Turkers on how to make better hits and how to get better results?
Yes. Okay, I can try. It was a while ago. Quality control. Yes, they helped us realize that a large number of approved hits would be a good way to get high quality. And that it would be a very sharp defining characteristic of Turkers that tended to always work in a very conscientious way and had been doing it for years, and other Turkers. Not to say that those with only 10,000 approved hits wouldn't do a good job, but that there would be more of a guarantee. We thought what we would do is monitor the hits as they were coming in, and so one of the most important things is that the way we indexed the data and ran the model, we did not need to have every annotator do every instance. But we're going to get much better estimates of annotators' accuracies if they do more, and we have more data from an annotator. So we wanted to encourage annotators, the Turkers, to do as many hits as possible. And that was something that we went around and around on, and really the Turkers kind of solved it for us. So Bob and I thought originally that we would start out with a lower cost per hit, and the more hits they did, the more money they would earn. And that's because once you have done a few hits, you kind of have, the word senses would be there on each hit, but you get used to it and you kind of know all the senses, and it's very easy, you know, after a while because they're in your head. When you first start, you have to kind of memorize the word senses. And so it was a very big load on us to design something that would either automatically up the rate that they were getting paid at, or that would do it in a fair way with some manual intervention and all this stuff. And they basically suggested that, now I'm forgetting, it was a combination of things, but we decided that we would just make very clear in some very short instructions that it's going to be hard at first, but please do as many hits as you can, and the more hits you do, the easier it will be because you'll know the word senses. And writing, it's very short. I actually have, I had a slide that showed it, and I can't remember if we put it in the paper. It just takes up so much room, but relative to the whole page, the instructions are actually very short. So one of the things they helped us with is iterating over the instructions so that they were very clear and they got the point across. And I can't really think of anything else off the top of my head, but those were some of the things that helped us in discussions with the Turkers.
Okay. So I'm tempted to ask you just a quick comment. I'm wondering, as you know, so ever since, so basically we finished the work in 2008, and so I was convinced that these models were sort of really the way to go because they give you so much more information. And these models have been around for a while, and Bob has been proselytizing at least since 2008, and you also have been publishing quite a lot of. So I'm wondering, why do you think it is that these models are still not really, most people, even now, especially considering that these models are really designed to deal with a large number of annotators, Turkers, and which is becoming more and more prevalent. Why is it that these models are still not as widely used? Most people do annotation still use some coefficient of agreement or the other.
Well, I'm not the person to ask. I can say that there was a very nice paper, NACL, I think 2013, by Dirk Hovey, about a tool called MACE or BAIT.
MACE.
MACE, yeah. It doesn't do quite the same thing, but it's using the same general approach of a generative model to eliminate all spammers, all the labels that are from spammers. And that's a toolkit, and I would suspect that that would be widely used. I think that's one of the obstacles, is that I think the people that collect annotated resources need the tools to make it easy to do that. But what do you think?
Well, I'm wondering, yeah, so part of the story is definitely that coefficient of agreement, there is, well, it's not just a software, but you get this one number, it's very easy to analyze, whereas, carrying out the kind of analysis that you showed here is more complicated, requires more time. There's certainly an issue of complexity but yeah, I'm wondering why there isn't more pressure. A few years after Jean published her paper in 1996, there was really a lot of pressure. People presented papers not giving coefficients of agreement, they were not going to be accepted. But I don't think there is quite the same pressure these days to analyze the results of an annotation effort using these. And I was wondering why that was the case. But.
Well, I do have a thought about that, but I don't want to go into the time of the next speaker. One of the things I think is really valuable is that we get a probability distribution over the labels for each item. And so there are items where there's no strong majority, but there may be two labels that are strongly competing with each other. And I think it's a fairer way to evaluate systems if you give systems credit for getting the next most closely ranked thing that's very close. So there's many more options for evaluating systems if you have this sort of data. Then you can also do more analysis of the type that Mark Liberman was suggesting that psycholinguists and other cognitive scientists and so on would be interested in. I think it might be that we have a lot of annotated resources for things that are easy to collect, that now are benchmark sets, that they don't need to be collected again. And a lot of the newer annotation efforts are for phenomena where the kind of model that you would have to write is difficult. So I have some data that's sort of simple, but it's still very different from this, and I'm trying to figure out how to write the model for it. If you have the kind of data that people collect with dialogue act tagging and links among the tags and all this stuff, then the model becomes very complicated, so that might be another reason.
Well, thanks. I think we should move on. Thanks to the next speaker for the patience, and let's thank Becky again.